Loch Eriboll in the far north of Scotland. And there, at the back of the valley, lies the spectacular ridgeline of the mountain Foinaven. This countryside, south from Loch Eriboll, across the ridge of Foinaven and down to Arkle, has changed the way in which we view tectonics, not just here in Scotland, but across the world.
Tectonics embraces the idea that different parts of the Earth move relative to one another. The most obvious modern manifestations of that are the plates, for example, where the European continent and North American continent are moving apart as their plates diverge. But tectonics also operates on a smaller scale. Faulting, for example, that occurs as the world's great mountain ranges are forming. Well, many of the ideas about fault tectonics come from places like this in the north of Scotland, and they reach back to the 19th century. My name's Rob Butler, and throughout my career I've been interested in the geological record of tectonic processes, but I started my career here in the north of Scotland, where I did my undergraduate mapping project in the hills to the south of Loch Eriboll. But I want to go further back than that, to the end of the 19th century, and we're going to follow in the footsteps of a hero of mine, a guy called HM Cadell, who worked this ground as part of the Geological Survey team in the 1880s. But before we start that journey, where are we and what's going on? Well, let's look at this map.
Those yellow rocks through the main part of the map are an area called the Moines, consisting of these highly folded rocks that once started life as a sedimentary pile but have been changed through metamorphism and deformed into these spectacular fold structures. And the Moines represents the roots of an ancient mountain range, generally called the Caledonian, that developed between about 450 and 400 million years ago. But not all northern Scotland represents the roots of this old mountain chain. Well, let's simplify this map a little bit. And out there to the west is an area we call the foreland, which comprises rocks that were not directly involved in this Caledonian mountain building activity. This foreland area, and the pink areas on the map, largely consist of ancient gneisses, generally referred to as the Lewisian. And separating the foreland from the Moines is a tract of ground that we now call the Moines Thrust Belt. The classic place to see the boundary is here at a place called Knocken Crag, and the Moines has been carried along a structure we now call the Moines Thrust onto sedimentary rocks that form the sedimentary cover to the old Lewisian gneisses. And here's the contact. But we moved ahead in our story because this is very much our modern understanding. Let's go up to Loch Eriboll, which is where most of this understanding was developed, up here. The geological understanding of the region really starts from research that happened in the area around Loch Eriboll, particularly on the eastern side of the loch. Up here, on Ben Arnabol. And this is the really critical contact. It was discovered by a geologist called Charles Lapworth, who recognised that Lewisian gneiss, rocks that were once deep in the crust, had been carried onto sedimentary ones. Here's the contact, there it goes, and the gneisses are carried onto quartz sandstone. We now call this structure the Arnabol Thrust. Well, the discovery of this outcrop and the recognition of what it represented in geology caused a revolution in the 1880s. In 1884, the director of the Geological Survey, Archibald Geikie, was shown these outcrops by his colleagues Ben Peach and John Horne, who had become convinced of Lapworth's ideas. And this is what Geikie said. When a geologist finds gneiss overlying gently inclined sheets of fossiliferous quartzite, shale and limestone, he may be excused if he begins to wonder whether he himself is not really standing on his head. It's interesting because this sentence shows the significance of the rocks and Lapworth's work. He changed the way Victorian geologists view the world, that apparently continuous successions had been messed around and repeated by thrusts which carried rocks in from the side. So although Geekie had initially been very sceptical about these sorts of ideas, there was no avoiding them when faced with outcrops like this. So he set about deploying his survey geologists to map out this region. Here's some of their mapping of the Arnabol area on the eastern side of Loch Erebol. And the map was put together by these characters here. Guy at the top, Ben Peach, who was the ideas guy, and the far more methodical John Horn, who compiled these maps and made them into a coherent story. And you can get an idea of what these guys were up against from Ben Peach's field map here, which shows not only huge amounts of detail, but also a lot of structural complexity, complicated geological boundaries, and these are even more evident when you look at a page in Ben Peach's field notebook, which is a cross-section drawn across this ground, showing the ideas of different rocks folded together, sliced together, a turmoil of tectonics.
So the east side of Loch Erebol is indeed geologically pretty complicated. Indeed, Pigeonhorn called this tract of highly faulted and folded rocks their zone of complication, and from 1885 their task was to try and track the zone down through the Northern Highlands. In this they were joined by a series of other survey geologists, one of whom was Henry Caddell. Now, Caddell had just joined the survey, he was only 25 years old, and his task was to map the area centred on Foinaven. So let's go and have a look at that landscape.
Looking to the head of Loch Erebol, the ground to the south doesn't look particularly rugged, but as you head into the hills, it becomes pretty obvious there's a lot of rock around here. The hillsides lead up above the rather boggy valley of Strathbeg, up onto spectacular outcrop. And pretty much all this ridge is made of these white quartz sandstones, much of it known as the pipe rock because of the burrows it contains. But it makes some great structures like this small anticline. It almost looks like you can surf on it. Crossing over those rocky slopes beyond and over the next valley, you reach the main ridge line of Foinaven, which is even rougher. But it gives great views and access onto this ground here. The stripes in the landscape are various layers of these quartz sandstones, and you can trace them around this corrie and up onto the flanks of Arkle, the next hill south, which separates Foinaven from the hills further south over in Assynt in the distance. But Arkle itself is also made of these quartz sandstones, shining white in the sunshine. And eventually this rugged ground eases as you come off the south side of Arkle down to Loch Stack. So that was the ground that Henry Caddell was tasked to map.
Now, of course, Caddell didn't carry around a camera with him in the field. In the 1880s, photography of landscapes was very much a multi-person activity. What he did, though, was to sketch in his notebook the views and, where possible, created watercolours to capture the geology that he saw in the landscape.
This is one of his first sketches in May 1885, looking up into the area he was about to map from the head of Loch Erebol. Though he's already identified the position of the Moines thrust, which he's labelled GSP. This will come up again shortly. But let's continue with Henry into this landscape and find him a month later in the next valley south in Strathginet, capturing the lumpy moraine on the valley floor and the rugged hillsides that rise out from the sides. It's quite a nice sunny day there. It didn't last. This is a view of this valley a few weeks later, as he says, in dull weather, but it shows the spectacular cliffs on the northern side of the Foinaven Ridge, and those rather interesting inclined layers of rock that form the cliffs. Again, more of those later. But Henry obviously made forays outside of his main mapping area. He captured this view of Ben Stack and Loch Stack in the foreground, perhaps on a walk-in to the Arkle area later on in his mapping, and he even went south into Assynt and sketched the classic hills. You can recognise Sullivan in the back.
So Henry was a pretty accomplished artist, and perhaps some of that's genetic. Reaching back to his great-great-grandfather, another branch of the Caddell family includes Francis Caddell, the renowned Scottish colourist. Francis was born a couple of years before Henry started his work here in the Foinaven area. So with this in mind, now let's go and have a look at what Henry Caddell recorded in way of field relationships in the mountains around Foinaven.
Well, we can start here in the upper reaches of the valley of Strathbeg. You can see the valley bottom and the river that's running from right to left. Well, Henry sketched this hill, but looking side on, so let's have a look at his sketch. Here we go, and we can recognise a number of dramatic features, particularly in the right-hand side of the image here, where you can see that fan-like structure. Well, let's look at a photograph of that cliff. And on this, you can see all these beds stacked up, one on top of the other. So we're looking at piled up sheets of quartz sandstone. Well, this is a motif that's repeated again and again through these hillsides. Here's looking across the lower reaches of Strathbeg. You can see the ridge of Foinaven in the far distance, but consider the immediate ridge opposite, and you can see a hillside made up of sheets of quartz sandstone piled one on top of the other. And here's Henry Caddell's sketch cross-section through some of that, showing the yellow quartzites stacked up across some of younger rocks shown in the sort of green and orangey colours in there. So he recognised stacking of strata. Now, if we step back again and look further along the ridge to the left, let's just do that. Get up onto the ridge and look along. And we're looking down along the ridge. There's the upper reaches of Strathbeg on the left there. And you can see sheets of these quartz sandstones piled one on top of the other. Again, here's Henry Caddell's profile through this ridge, and we can see that sort of idea in here, with slices of the quartz sandstone shown with that dotted symbol, intersliced with some other rocks, younger rocks, shown with little stripes of green on there. Well, again, he saw this sort of structural style again and again through the hillsides. We'll look at this same ridge from the other side, looking across from the Foinaven ridge. Here we go, looking down from Foinaven. We were looking at the right-hand sides just now of the ridge that we can see in the centre of the screen. That's Strathginet running through the middle of the photograph there, going out towards the left. So we're looking at a ridge there that's running southeast on the right to northwest on the left, bright white quartz sandstones. And here is Henry Caddell's profile, seen in his notebook sketch. Well, let's just zoom in on it. And he's representing the escarpments seen on the hillside as slices of quartz sandstone picked out and separated by things he's labelled SP, which stands for slide plane. We now call these thrusts. And here they are. Well, the really dramatic representations of this type of structure are seen on the hillside opposite this one, which would be directly below the viewpoint that he made this sketch from. So let's look at Henry's watercolour again that we saw earlier on, looking down Strathginet. So we're looking out towards the northwest, and on the left there is this dramatic cliff with slices of inclined quartz sandstone. And here is his sketch of the geology that goes alongside his watercolour. Again, SP stands for slide plane. So he's interpreting all these panels of quartz sandstone as being stacked up one on top of the other, rather like a pile of dominoes piled up against each other. Well, here's a field photograph I took maybe 100 years after he was there, with the crags dusted after a light winter snowstorm. And here's my cross-section through that cliff section, with different parts of the quartz sandstone succession shown in different shades of blue, repeated again and again and again on a stack of thrust slices. And then at the back, running over the top in yellow, are the Moines rocks carried on that dashed line, which is the Moines thrust. Well, here's the cross-section in there, and you can see the result of this stacking process. Stacking these quartz sandstones again and again to make the mountain of Foinaven. Zooming in onto one of these snow-dusted hillsides, you can see the thrusts picked out by the snow, climbing up like that, repeating the stratigraphy again and again and again. So that's the geological structure of the ridge of Foinaven. Let's now look at the head of the valley, Strathgiant, over on the left, and look at some of Henry's work again. So here's a page of his notebook at the back there. The green and curly schist are the Moines rocks carried on GSP, the Moines thrust. And you can see various parts of the Cambrian sedimentary rocks stacked up beneath, along with a slice of gneiss. Here's what this cliff looks like in here. It's quite dramatic countryside. This is my own cross-section through there, again showing the Moines on top and a slice of Lewisian, together with these various piled up pieces of the quartz sandstone, here called the pipe rock in light blue, and various younger rocks as well, caught up beneath the Moines thrust. And within the BGS archive of photographs, they have an image here of some of the field geologists working up here. Presumably one of these characters is Henry himself, but we don't know who these characters are, and the photograph doesn't have a high enough resolution to pick out the individuals. Though the lack of a portly character in there suggests that at least one of them is not Ben Peach. Either way, we've got 4 geologists here stood on the Moines thrust, just east of the Foinaven Ridge. So we can return to one of Henry Caddell's cross-sections through there, again showing these structures with folding and faulting, slicing the rocks together beneath the slice of gneiss and the Moines rocks that run over the top. So how did Henry consider this thrust slicing to work? Well, here's another part of his field notebook for the same structure, seen side on, going back into the cliff section, showing various stratigraphic units. The quartz sandstones, PR stands for pipe rock, which is part of the quartz sandstone succession, shown uncoloured but dotted, and then various other parts of the stratigraphy sliced together on those rather steeply dipping thrust faults, and then the whole lot capped by those uncoloured units, which are the Moines rocks running over the top. So that's how Henry envisaged the thrusting to work. And in this he'd been guided, perhaps by an image that had been drawn from him, that you can find in Ben Peach's notebook. Here is a page from Peach's book, and you can see his idea of how thrusting worked when it was operating in a package of strata. Consider that lower part of the diagram, and what it shows here is Peach's notion that before thrusting the rocks were originally continuous and subhorizontal. So we can just animate his ideas. Here's his pre-thrusting situation with the strata horizontal and continuous, the line of future thrust shown by those diagonal pencil lines, and the act of thrusting stacking the strata up like this. And that structural style was taken forward into the cross-sections that appeared subsequently in the memoir about the Northwest Highlands geology. And here's the cross-section through the Foinaven Ridge, almost certainly drafted by John Horn, based on the fieldwork and observations of Henry Caddell and the ideas of Ben Peach. Well, let's just zoom in onto the more detailed part of this here. And what it shows are a series of thrusts that I've just animated here in red that stack together the quartz sandstones. And this stacking process is only skin deep. It's detached on a major low-angle structure that the Geological Survey termed the sole thrust that separates the stacking process in the sedimentary cover from an intact pile of rocks beneath that include all the gneiss basement of the Lewisian. So we have stacked quartz sandstones detached and emplaced upon the intact Lewisian basement. So the stacking process is only skin deep, and all of this occurs beneath the overriding Moines thrust, or as Henry Caddell called it, the GSP, or Great Slide Plane. So this diagram summarises the ideas and results of Henry Caddell's fieldwork that he conducted in 1885 and 1886, although if you look at his notebooks, he appears to have cracked the problem within the first couple of weeks of fieldwork in the early part of his season in 1885.
So let's just take a little aside from the Caddell story and just ask the question, what do these thrust zones look like close up?
So here's one of these thrust zones seen in a stream section. So let's just pick out the thrust. Here it goes. It's a good job that person's keeping her head down. Well, let's just zoom in and have a look at what the fault surface looks like. Here it is, and it's got this rather strange blue mottling and that yellow pastiness to it. And we can see this blue mottling here as well. Well, when I was mapping this ground, I referred to this sort of texture as bruising. It looks like the rock's been rather badly damaged. And indeed it has. When you take a thin section of this and look in detail, this is what you see. This view is just a few millimetres across, and you can see that the rock is entirely shattered. It's a type of special rock that we call a cataclysite, grains formed by breaking. And the way in which we think these types of materials form is by repeated shattering events as faults stick, slip, and continue to move in that fashion. Between each slip event, the rock bonds itself together, and then the rock is rebroken as the fault slips again. These slip events would have made tiny earthquakes. So the act of fault slip and the generation of the structures that we see on the Foinaven Ridge and adjacent mountainsides are formed by the repeated action of thousands and thousands and thousands of small earthquakes, collectively slipping the faults and building up those dramatic structures.
Well, let's return to Henry Caddell, and he didn't want to leave it there with just a simple description of the structures. Rather, he wanted to understand how the structures that he saw in the outcrops at Foinaven came to be. Now, in the late 19th century, pretty much all understanding of structural geology and tectonic processes came from the Alps, and there was an idea in play that fault structures, where they occurred, were relatively minor and just developed as a consequence of a folding process that had gone too far.
This idea had been developed by Albert Heim in Switzerland in the 1870s, and here are his diagrams. Well, perhaps the easiest way to see what's going on is to animate these again. So we can see what's going on here. Here's his setup with a simple fold pair, and we can track what's going on by looking at the behaviour of those two blobs, yellow and red. So as the deformation continues, the red blob overrides the yellow like this, and the fold becomes sheared out along a structure here that eventually becomes a thrust fault. So for Heim, thrusts were a consequence of folding, and if you look at alpine outcrops like this, you can get some idea that that's not completely balmy. Here's a large-scale hillside in the French Alps showing the type of fold structure through which thrusts would have initiated. And if you go elsewhere, such as these locations in the Jura, you can see fold structures rather like the one we've just looked at, but this one's been broken through by a thrust fault that comes through here. So it was outcrops in the Alps that had inspired Heim to propose his model. So are these ideas from the Alps universally applicable specifically to the structures that we find in the Northern Highlands?
Well, Henry Caddell's mentor, Ben Peach, had the idea that faults form just by simply snapping through layers. Indeed, his sketches in Ben Peach's notebook showed that, and Henry used those ideas when he drew cross-sections and interpreted outcrops as well. So how could he investigate how faults actually form? Well, now we need to introduce a little bit more about Henry's biography. He was the great-great-grandson of William Caddell. Now, William was one of the three original partners that set up the Carron Company Ironworks near Falkirk, which was one of the centres of the Industrial Revolution in the central belt of Scotland. And Henry's branch of the family had continued the business. His father was a leading industrialist in the Forth Valley. So Henry was very familiar with science and technology, and he wanted to apply those ideas to understand the geology of thrust faults. He set about recreating the types of structures that he'd found in the Northern Highlands through experiment.
Henry carried out his experiments in just 1 week in January 1887 in his backyard outside his house in Grange. He wrote about his motivations a few years later and said, "When discoveries are made in various departments of physical science, it is usual, if possible, to try how theories squares with facts, and such branches as electricity and chemistry, the experimental method has produced the most important results." So Henry wanted to experiment, and there is his deformation rig. The deformation rig consists of a rectangular box about the size of a coffin. The two long sides are fixed, the two short sides are squeezed together using a vice, squeezing some material that acts as an analogue for rocks in between. And here it is. In this particular experiment, he squeezed together materials to make fold structures. Well, we'll come to that in a minute. Let's look at his first important experiment, which was to test the ideas that he developed with Ben Peach for the idea of thrusting, and particularly whether thrust could be formed without precursor folding. And here are the results. You can see that the materials caught between the vice have been pushed up one on top of the other, repeated by thrusts. Let's look at a detail of this. Here we go. And then for clarity, Henry traced over the photograph and made a watercolour of it. Here we go. So we can see the layers of material stacked on top of each other. Now these materials are not rocks, they're an analogue for rocks, which consists in his case of damp sand and plaster of Paris. The plaster of Paris, which is white on the photograph, is key because he laid that with the damp sand and left it to set, creating a brittle layer, rather like a layer of crisp bread within his otherwise damp sand material. And the plaster of Paris layers snapped and behaved brittly to localize thrusts. In other experiments, he used foundry loam, which presumably he borrowed from the local ironworks, foundry loam being a mixture of sand and clay, and he could use that also to create thrust structures. Let's look at a few more of his experiments. Well, here's another one with different layering, and in this case he's created some fold structures and thrusts together in the same experiment. But he also wanted to see whether he could create folds alone. Here's an experiment that does that, which is rather like the one we saw in the opening photograph of his experiment rig. And to create the folding, he wanted to inhibit the faulting, so he built his model upon a sheet of rubber, which simply buckled, with the layers of sand and clay above following the fold structure. So a set of different experiments with different materials that generated different structures. And in doing these range of experiments, he was able to identify the different materials that controlled thrust localization. Sometimes rocks folded, sometimes they thrust, depending on the rheology, material properties of the materials involved in his deformation rigs. Regardless of these varieties, all of his experiments showed that deformation structures like these were formed by lateral contraction, in other words, pushing the two sides of the area together, in other words, horizontal compression.
Henry's experiments have continued to be hugely influential. Indeed, they've established a branch of structural geology, of analogue modelling, which continues to the present day. But I think we can learn quite a lot from the way in which Henry went about his experiments, because he tried to recreate a variety of deformation structures, and we can use those to understand some of the structural variations that we see in places like the Alps today.
Here's an example from the outer part of the French Alps, where we can see various stratigraphic units in the different colours thrust up on top of each other. But actually the structural style varies across this area. Let's just look at part of this in the central part of the cross-section. Now we've already seen part of this cross-section already from the Arve Valley in Haute-Savoie. And we look at the cross-section in here, different layers are deforming in different fashions. So the light blue layers are deforming differently from the green. Let's just look at two parts of this section in here, showing this classical fold structure in here, which we can just trace out, showing that this particular layer, which is a Jurassic limestone layer, has been folded into this fold pair. And that behaviour contrasts with shallower parts of the stratigraphy shown in green, Cretaceous rocks down here, where these units have been thrust together like this. So different units are deforming in different ways, as predicted by Caddell's experiments. Different rock properties, different behaviours. So if we come back to this regional section across the outer part of the French Alps, we can see that different places are deforming in different ways. Maybe the outer part is deforming by thrusting more readily than the central part of the section, where folding is also important. So Caddell did not try to mimic individual explicit structures. He really wanted to demonstrate how structural styles vary depending on the rock materials. Notice that his experiments also involved detachment, so the base of his coffin box isn't deformed, the clay and sand are being shunted over the top, and the same is true for these sedimentary units in the outer part of the Alps, shunted above their crystalline basement.
But I think a major impact of Henry Caddell's fieldwork and experiments was to open our eyes to see deformation of rocks, rather like an industrial process, where rocks from an adjacent area have been brought into a thrust belt and processed by thrusting and folding into the complex structures that we see today in the Moines thrust belt and elsewhere.
So returning to his experiments, we can just animate this process. Simply layered material being incorporated as the deformation migrates towards the right here. So we can return to where this all started on the southern end of Loch Erebol. It's the outer edge of the Moines thrust belt, and so it's the edge of the ancient Caledonian mountain belt. Let's go and have a look. Here are the fallen strata. We can see the gneisses of the Louisian at the bottom of the valley, overlain by Cambrian quartz sandstones that in this particular view are not deformed, but as we trace them in towards the left, which is going east into the Moines thrust belt, we can see that these Cambrian quartz sandstones are pushed up onto themselves in a similar fashion to that created by Caddell in his experiments. Well, we can see these types of behaviours in modern mountain ranges as well. So let's go to the edge of the Himalayas. Let's just show where we are. We've got the Himalayas running through the middle there in the snow. Behind, in the top of the image there, you can see the brown ground of Tibet around the curvature of the earth. And in front of the Himalayas, the green Indo-Gangetic plains of the Indian subcontinent and the rivers flowing out from the Himalayas. And this system is developing because the whole region is being compressed as there's plate convergence, as the Indian continent to the right is being pushed into the rest of Asia in the north on the left. Well, let's zoom in and look at part of the active deformation front down here in what is part of northern Pakistan. Here we go. We can zoom into this box in here, and we can see the Jhelum River there running through the centre of the image, flowing towards us. To the right of the Jhelum River, the plains are not deformed, everything's flat-lying. But if we go in a bit closer, we can see that sediments deposited only a few thousand years ago by the Jhelum River are now standing up on end as the bulldozer of the Himalayan origin is shunting southwards into the plains of the Punjab. So this is the active deformation front. It changes as we go along, so let's step back out again and continue a little bit further along and then zoom in again to here in an area known as the Salt Range. We can see that the deeper parts of the sedimentary succession are carried up onto sediments of the plains of the Punjab. Let's just add some ornament to this by zooming out a bit and adding some rocks, and now we can build our cross section. So we can see these pink rocks, which are actually lower Cambrian salt deposits, carrying their sedimentary cover up onto the yellow rocks, which include yesterday's sediment along the Earth's surface there. And to zoom out a bit further, this is how this system works, with sedimentary rocks in the pink, blue and orange carried up onto the yellow rocks on the margin of the Himalayas. Again, as Henry Caddell showed, these particular structures are detached from their underlying crystalline basement, which is shown in grey here. And all these rocks shunted southwards as the Himalayas are forming and India is converging with the rest of Asia.
Thrust tectonics, where originally gently dipping strata are pushed one on top of the other to make mountain ranges, is seen as a major tectonic process. That insight comes to us because of the work of Henry Caddell, not only his great experiments that he performed in his backyard in Grange, but also from his inspirational fieldwork that he conducted in these dramatic hills in the Northern Highlands of Scotland.
By visiting the Erebol area, we can follow in the footsteps of Henry Caddell. For thrust tectonics, this is where it all began.